So remind me, Diego, is your background originally in architecture?
Yeah, I got a bachelor's and a master's in architecture.
Yeah. Wow.
Yeah, up until Mindesk, I was working at architecture firms.
Oh, yeah. Well, I knew you were working at WRNS, but increasingly I meet people who are focusing on technology innovation in design firms, and their background is not actually architecture.
Mm,
They're hiring people from tech backgrounds rather than design backgrounds.
yeah.
Yeah,
Interesting.
interesting. So changing the mix within the firm a little bit.
Yeah, I think that people that can kind of be the mediator between two different fields is very
Yeah,
valuable in general.
yeah. I mean, obviously they have to have some sensitivity to design and to the practice of architecture,
Yeah.
but they don't have like degrees in architecture, and not licensed or anything. I think technology is a bigger part of the architecture education now, of course.
Yeah, it
So,
certainly is.
yeah, everybody's a bit of a technologist.
The final reviews these years, the last 5 years
Yeah,
or so, are
yeah.
pretty wild to see compared to what I was making coming out of school.
Mhm.
And with all this new technology and construction and stuff,
Yeah.
it's not as crazy as it was once looked at because it's a lot more possible to make these kind of things.
Hi. Well, I want to welcome. I can see Mark Douglas Cooper. Thanks for joining in.
Thank you all. I look forward for this.
Good, good. Yeah. I know you have a long-standing interest in design technology, Mark.
Yes, I do. Yeah. Yeah.
Are you now practicing on your own?
I just finished my master program.
Congratulations.
Thank you. Yeah. Yeah.
And where was that?
California College of the Arts.
Oh, great. Yeah, CCA is such a good
Yeah,
program.
CCA.
Mhm.
That's great. Yeah.
It's cool.
Yeah. Thank you. Thank you.
It's probably a good time to be studying.
Absolutely. Yeah. Yeah. Actually, virtually was more interesting because we could attend like conferences in Europe and Canada.
Oh, yeah.
So it's crazy. Yeah. It's
Yeah.
more time to do things. Yeah.
Welcome, Maria. Thank you for joining in. So we're just going to take a couple minutes here to let people gather. And then we're going to start and people can continue to come in as we go. Specifically, we're waiting for two of the co-presenters to join in, Jillian and Jeffrey, but they're going to present after Diego, who's already with us. So that won't really delay us.
Works for me.
Pardon me?
It works for me.
Good. So Maria, are you an architect? What is?
Yes, I am.
And where do you work, or what kind of work do you do?
I work in residential.
Uh-huh.
We work with a lot of big developers, and we have offices in a few different states, but I work on the Northern California homes for the most part.
Oh, I see. So what firm do you work with?
KTGY.
Oh, sure. Yeah, that's one of the big ones. I guess
Yep.
HKIT is considered to be sort of similar.
I think so, yeah.
Yeah. Well, there should be lots of work for you in California.
Oh, there's plenty, and a lot of single family housing is booming this year too, after slowing down last year.
Uh-huh.
It's pretty exciting, a lot of work coming in.
Glad to hear that. Hi, Mark.
Hello. Uh-oh.
How about you, Cooper?
Sorry. Hi.
Yeah. How about you?
Wrong headphones.
Yeah. Are you an architect also, Cooper? Maybe your mic isn't on. Okay, so I think it's fine to get started now. My name is Dave Alpert, and I'm a licensed architect. I no longer practice architecture. I lead a design technology firm. And in fact, that's how I met Diego. So Diego Taccioli is both an architect who had a lot of experience at WRNS and an entrepreneur, an inventor, an innovator. And he's going to talk about the work that he continues to develop with his own enterprise, Slicelab, which involves a lot of 3D printing. And that's the thread that ties together Diego's work with the work of the other co-presenters, Model No, like Model Number. And they're focused more on a furniture scale, whereas Diego works on all kinds of scales, from buildings to, I understand, ski bindings, now that he's based in Denver, which sounds pretty interesting. So to tell you a little bit, just very briefly about the Design Tech Committee, we have meetups every month. That's always on the third Wednesday from 5 to 6. We can't wait until they're face to face, but right now we're still enjoying the fact that at least they're on Zoom. So thank you to the AIA. At the end, I'll say a little bit about the upcoming ones. Most importantly, the next one on June 15th will focus on return to work and the design technology that's supporting that new way of working now that we're hybrid. Okay, so do you want to start, Diego, and kick it off?
Yeah, let's do it. All right, let me know you can see the screen. I'm just going to share it here. Can you guys see the screen? Awesome. All right, so like you said, my name is Diego Taccioli. I have my design practice called Slicelab. We're basically an experimental design studio that specializes in digital fabrication and consulting. And my co-founder is Arthur Zulai, which may or may not be listening into this. And what we're going to go over today is basically how we constructed this concrete coffee table using 3D printed pieces and just a lot of test prints and kind of studies. But before that, I just want to go over kind of what we do and a few test projects that kind of relate into the back end of the presentation. So Slicelab basically bridges the gap between product design and architecture through digital fabrication, like I mentioned. So while we work a lot in architecture, we have now gotten into a lot more zoomed in design, so product design, some really small pieces versus large pieces, and furniture design. Generally, the types of fabrication we're familiar with are the majority of what most people understand, which are the three different types, which are subtractive manufacturing, which is like a CNC mill, as some may be familiar with. There's additive manufacturing, which is 3D printing and all 7 forms of that. And then there's formative manufacturing, which is like injection molding and traditional styles of making products. All these 3 are starting to bleed together, and we're trying to pioneer what we can with kind of combining these in our own experimental way. Generally, our software workflow are these 6 softwares and kind of in the order of which you see them. So Rhino, Grasshopper, as some of you may know, go pretty well together, as well as ZBrush. And then the Autodesk suites like Maya and Fusion 360 go hand in hand, as well as with Mesh Mixer for post-processing work for 3D printing and creating watertype files. So I just want to cover DFAM, which is basically designed for additive manufacturing, and how generative design and topological optimization is starting to be quite a force within this realm. There is generative design. There's that has been seen mostly solid for the most part, and it's starting to become pretty useful for manufacturing in all different like careers and applications. And now there's a lot of more seen with lattice design and kind of both, where generative design is basically like something that you can do a lot of customizing, you can do assembly consolidation, you can do lightweighting, while topological design or optimization is basically like having a set geometry, like let's say this bracket, and then kind of reducing the weight. And generative design, again, you can kind of set some certain parts to be fixed or set, and everything else basically grows from it. And what we're trying to do is learn the most about the two and try to combine them into something a little more useful. So I just want to go over 2 case studies before we go over the full thing. This is an AIA learning session, so I want to kind of talk about how we generally go from concept to form. This is a shoe that we designed a while ago for a 3D print company called Origin, and they were supposed to be using it for kind of like what you've seen with Adidas Futurecraft 4D. And the way we kind of work is with concept and kind of move forward from there. So the Roadrunner is kind of like this lightweight bird that has a very interesting skin pattern on its feet, and which allows it to be light and quick and unnoticed. So one of the things we started to develop is our own voxel for understanding how we can use compression and rebound. And what a voxel is basically is a 3-dimensional pixel or volumetric pixel. So with programming our own voxel into what would be a shoe or a midsole, we map a foot imprint with a certain amount of forces that we were generated through a set of colors. So basically, you can kind of relate that. Let's say the red is the hardest point, which I can't remember the exact newtons of which we put into the software. But this goes into our parametric design, and the amount of torque, beam thickness, scale, overall height, shrinking, and rebound are basically calculated into this using this image, as well as some other factors. And as you can start to see, it's kind of like a hexagonal Voronoi 3-dimensional cell that creates this midsole that was designed for this shoe that is not a real product right now, but was on course to be one. So here's just a few renderings of it. Here's some close-ups of it being printed with 4 different types of TPU and resin mixture for different applications to see which ones would work the best. And here's some final images of what we got, kind of showing the lugs on the out pattern here and kind of the midsole opening up here for the opening.
So Diego, that shows the scale of those voxels, right?
Yeah, exactly. So each one of these would be a voxel. Almost each one of these. It's actually like a square a little bit further past it.
And how did you come up with the name of the voxel? Is it like a volumetric pixel or something?
Oh no, I didn't come up with that. It's just it's kind of like a term used in this industry a little bit more. I just say it's a three-dimensional pixel, so people sometimes not sure what I mean.
Yeah, so everyone, you're invited to just raise your hand, ask questions. You can also use the chat if you want, and I'll monitor that.
Yeah, so let me just kind of go through these 2 little case studies, and then I'll go into the main one. What we most recently did here was it's like a mountain structure concept for a 3D printed snowboard binding, where basically we create a combination of a lattice with the concept of mountains in the areas of which we need the most structure for. And using this topology optimization for the lattice, we were able to calculate the deflection, the yield, and the shear, and basically create thicknesses where they're needed, the orientations where they're needed, and the amount of material which we can take out. So in this particular one, we figured out that we could take out this bottom part here and create this geometry, which we later 3D printed with a new high impact material that hasn't quite been released yet, but also has good thermal property to it. And it's made by Loctite. And again, our partners at Origin were working with us on getting these printed. And this is like a real photo now. I actually went to test ride this last week, just kind of great. It seemed to hold up pretty well. So yeah, that's kind of like a taste of what we were working with in terms of lattice and topology optimization. But more importantly, we're trying to get into a little bit more research done on concrete complex forms. So here's some precedent studies we've seen before that we were really interested by. Things like this, where there's a hole in between, or even all this stuff that's modular and then later connected. Zaha's wall texture here. This kind of stuff isn't normally seen in architecture without paying a lot of money or even possible to do. So these days, there's just a lot more going on with it. So we took our own version of how to create some concrete forms. Now, this is an existing developing concrete print process, which is basically a large 3D printer that extrudes concrete through a nozzle. While this is, very impressive for sure, there is just so much more to be explored so far, because unfortunately with FFM, which is basically a type of printing process, which just means that it's being extruded, you can only establish so many types of forms with concrete or clay or any type of mixture without using formwork, because unfortunately it's just really heavy and gravity seems to take its part, and it's not solidified. Plus, it just doesn't have a rock hard. It doesn't come out rigid. Of course, it needs to be mixed, it needs to dry, it needs to cure, etc. So what we started is with creating a few different forms that we wanted to pour in concrete using 3D prints. So we started with a simple shape like this that was able to have 4 flat sides, which create the openings for the cavity. And then we bolted together 4 pieces of PLA, thermal enhanced PLA plastic. And from there, we started to kind of experiment with different materials. So the classic Quickcrete, you can find it at Home Depot. Circrete, which is like a finer based concrete for more crafts, but it has a really good detail. And then Circrete, which is a very strong, high performance white concrete that has a very strong tension compared to, like, the tension ratio compared to other concretes that have almost no tension. Also, we added some additives like alkaline resistant fiberglass, super plasticizer to make it more flowable and to have less water to make it stronger, and then chopped basalt fibers as well. So we started kind of playing around with the mix of all these. And we also did, one last thing, is we coated the insides of all the molds because we wanted to see what the difference of applications would be. So sandpaper, which is the most common you see with 3D printing, Z-epoxy, which is a epoxy pigment, and then there's acetone vapor bath and a 3D print specific epoxy, which is called XTC 3D. So that being said, sorry, please go ahead.
Oh, I didn't mean to interrupt you. Diego, there's a question from Mark about what strategy is approached to generate the data inputs for the voxels. I realize we're going back a little bit.
Can you repeat the question?
What strategy is approached to generate the data inputs for a voxel? Like, that was kind of complicated, the little diagram you had, and you had different forces and stuff going there.
Okay, yeah, so the data, there's a bunch of things that you can implement into parametric design. So let's say one was that the minimal pipe or cross section of one of those lattices could not be lower than 0.25 because it's not going to print, or it can't be higher than 1.2 because otherwise it's going to connect to the adjacent pipe. So stuff like that, where you basically start putting parameters in. We put in force loads that we found in like papers and research. But again, everything in parametric design is unfortunately, it's only as good as what you put into it. So while we do have very much confidence that the things that we're doing are accurate, a lot of times there's just neglected areas of which parametric design can have kind of the Achilles heel of something. So it's kind of hard to answer that question directly without showing you the definition or script. And then unfortunately that's going to be too boring or take too much time.
But I mean, that's perfect. It brings up the really good point that even if you have a great model, like inputting data in order to create something like a voxel, that it's only successful if the data is the appropriate data that's needed.
Yeah, so we did do some tests on that particular voxel in terms of compression, shear, rebound, and torque, and we started to see what needs to be achieved depending on what is being acted on it. And we took that information and all those numbers and tried to apply it across the board in our own versions of calculations solidified.
Cool.
All right, so I just wanted to cover this real quick. So these are the post prints, or basically the prints after leaving post process. So the sandpaper looks pretty normal. It's kind of like that white chalky look. The Z-epoxy and the 3D has a shinier look, and the vapor bath had a really interesting effect on the plastic because it basically made it soft and malleable, but it did shrink it. And you can start to see the differences, what happens after they're been poured. So the sandpaper had the most amount of connection to the concrete and therefore broke the most, and also seemed to kind of suffer the most weight load in terms of being able to stay connected. The Z-epoxy kind of had this snakeskin material like finish after it was excavated from the print, and then the last two kind of had a pretty good rating. So we kind of went with this piece as our next point of which to keep researching. And one interesting thing is we were looking for this cratering, this kind of like moon cratering that you see underneath. This is basically all the air pockets trying to get out, which we're not able to get out. So we went with this slurry, and we started to design another form. It's basically a smaller table, trying to grow up to that same size. So this thing's a lot smaller. It's kind of like the same size of like a small ironing board. So again, we printed two pieces or two sets of pieces that we were going to pour all from the top here, and they would all basically solidify underneath here, creating the top surface as a very smooth piece. And after we made a educated guess on what the two slurries should be, again, we're going with this particular one that we found to be the most valuable. We started to see the exact amount of stress that were starting to happen on both these thin limbs and the actual 3D prints, and where they started to break because of a hydrostatic pressure, because of bait, and because of off-gassing, and et cetera. They really started to rupture on their own. These aren't like broken by me or anything. So you can start to see the material that's coming out of it now. I kind of just put a small iron on there just to give you a reference. So these seams started to become an issue. The texture started to become an issue, so we started to adjust accordingly. So for the final shape, we started designing through the sense of profile. So we kind of want this look to have it in terms of what the final is going to look like. So we started with a Maya design that was completely sculptural and how we wanted to make it, and then we finished with something that looks a lot more like this. And we kind of went back and forth between Maya and Fusion using the generative process in Fusion 360. And here's just kind of a quick time lapse of a lot of the different forms we started playing with and what we ultimately landed on. So eventually, once we were happy with the general section that you saw a second ago, we brought this into Fusion 360, and we put the adequate forces on it for the overall weight and the additional weight that we wanted to add. And we put 3 major points of connection so that our piece would basically use the generative design to ultimately land in these points versus how it is currently. And the way we set up the generative design is we designed a surface that we wanted. That's the green. The red is areas of which the generative design cannot grow into. And then the yellow is the existing, or basically what we implemented. And then this kind of shows what we got here versus what we started to implement between the previous one, and then adding a lot of the thicknesses that we had to assume at that scale, even though we know that we had a really good feeling that we can go a lot thinner than that was suggested to us. So here's just a kind of like a quick video of like the generative design and where the forces are and how thick it started, and then kind of how it solidifies down.
Yeah, really interesting. So of course, as I look at these smaller objects, I'm questioning like, so how does this scale to the size of a structure?
I will be getting there. It is a good question. It scales. Let me just get there because it's kind of hard to. First answer is I don't know yet, but we are looking to do that.
Yeah.
So here are some of the generative results we got. This particular one here was an evolutionary solver, or basically something that was topologically optimized to reduce as much weight as possible. This we thought was a little too thin, so we ended up picking one of these and then redesigning it to create a form that we were happy with. And then what we did was we made a prototype at half scale, same exact strategy, except this one was supposed to be identical to the full scale one. So we put these ribs across the bottom so that it would sit flat when it's poured, but also to give it additional structure. We post-processed all the pieces with the exact thing we talked about before with sanding and with adding the epoxy. And then we went ahead and started mixing the slurry that we designed as the best for us for this type of project. And we had it on a shake table. And after, this is kind of like the aftermath of, or not the aftermath, but this is what it looked like right after we poured it. And again, there's bolts all around the edges, some additional clamps in areas that started to bust in the middle of the pour. And we just kind of took notes from there. Like the previous one, it was not created to be demolded. So we just took a few blow torches to this to try to get it out, because we didn't really know a different way without absolutely breaking it, the actual piece, which is actually pretty fun, as you can see a photo of me there. We did have some burn marks, and we lost one of the legs here. And I'm not entirely sure that's because of how thin it was necessarily. I think we kind of bumped it, but that was somewhere where we decided to bulk it up anyways in the future. These are the top and the bottom views of the molds before and after. We painted this blue just to kind of establish the line between the smooth and the porous, and also kind of to hide the fact that we had to glue it back on, which is kind of see right there. And then lastly, before the final, we made a full-scale partial mock-up. So this is just like one of the legs that is part of the full scale, and we kind of analyzed the way that it flowed into the cavity with time lapse and with temperature gauge. We also started to implement a drilling process, because as it would off gas and heat up and the hydrostatic pressure would increase, you could feel the molds move in pressure points. So when there was a bubble that we were able to feel only after being able to do this a bunch of times, we were able to drill in there, like alleviating that piece and allowing the concrete to kind of come out, but not enough, obviously, to leak out. And then the glass was very helpful or the plexi was really helpful to kind of see exactly where the flow issues happened and how they worked. Let's see here. So this is the full scale mock-up, a little bit closer. You can start to see that the bubbling here was a little bit too massive, and the texturing at that scale started to be a little bit distracting to the point where it was not ideal. Even the top piece where it was supposed to be flat was very chunky, and the separation, because of the stress, was able to really significantly move it. So again, we had to go back and reinforce the shape. So this is the final shape. We broke it apart into 23 pieces, all of which were rectilinear in form, because we did have to print it on a relatively standard printer, which was one of our main goals, is not to use anything overtly fancy to create something of this complexity. And these are all the pieces in the exact orientation of which they printed for them to have the strength that we needed in the direction that we needed, because that's also important. These are the full prints, kind of all lined up right before the assembly. This is the assembly that we made in this exact order as well, because lining up the main edge was relatively easy in comparison to lining up all the other side pieces. And from here, we had 3 major cavities of which this was poured into, 10 legs and one major final cavity. Again, we had the structure all at the base to keep it all flat, and structured these connection points even more than normal, and we even added additional microstructures within the prints, which came out somewhat well. I can stop here for a second if there's any questions. Otherwise, I'll keep going. I just don't want to talk the whole time.
Yeah, I wanted to question you about, obviously, the complexity and the difficulty of designing something like this. So, I mean, unless it's one custom object with a very high price tag, then it's a necessity for there to be some scale at which it's produced.
Yes, exactly. So the result of this entire experiment was to figure out how the amount of strength and material and geometry that is needed to create reusable molds in the future. And that's kind of our second part of this that we'll hopefully go into. Unfortunately, it is for this experimental piece of furniture, it is unfortunate we had to break all this apart, but it also was a lot more economical for one to actually pull it off than to have what would have been at least 56 different parts that had to be used specific material. So this mold, I believe, was $8,000, but it could have been $25,000 for reasonable pieces.
Yeah.
And what we're not doing right now is we're not testing the 3D printing. We know that it's possible. We're testing the material. We're testing the finite material of concrete done in this manner, of which has no rebar to keep in mind. And I will cover both that and what we mentioned earlier in 1 second. So we started pouring the concrete, after which we set up all these jigs so that the concrete couldn't move. And at first, everything kind of started to seem like it was working pretty well. In fact, this is a photo of it being poured immediately after it being poured, where everyone kind of walked away. We had a team of 9 at Concrete Works. They were our partners that's in the East Bay. But within maybe 2 minutes, all that pressure that I've been talking about before started basically hitting it everywhere. It was almost like a movie where all the valves start breaking. So we had all the teams either super gluing, clamping, taping, putting a rock on one piece, all the things that we were expecting kind of came out all at one moment, and we weren't able to drill fast enough. So we basically had to drill a lot to start to alleviate this thing. And we eventually saved it. It looks a lot worse than it is, but it was obviously an extremely high pressure moment that we learned a lot from. So eventually it did all work out and it was fine, and we didn't waste $8,000 on this mold for nothing. But we did have to obviously post-process the base to make sure it was flat, like I mentioned. Some of the concrete wasn't doing that before, and then we had to excavate this thing out of its mold because they were not removable. So all the bottom pieces were chopped out or basically chiseled out, and then the top piece was all one piece that was very easily taken off. And that was because we treated this piece the most because we wanted it to be the smoothest. And that's also most importantly where all the bubbles did not stay, because they're trying to rise up through the legs and out, or through the holes that we provided for them as we were pouring. So the table actually came out relatively well. You can start to see the striations at the bottom here of the 3D prints, and then the air bubbles here. And then this is the table on its side right before we go to hit it with the wet diamond sander. So it went from being relatively striated from the 3D prints that you guys may or may not know have when you print them with FFF extrusion, and then it went pretty much to a mirror finish afterwards, which was obviously was pretty nice, and you can kind of see that after it's dried off, kind of that matte, really nice concrete there, while you see the juxtaposition with that porous moon-like surface there. Here it is, just waiting on the table. One other thing I forgot to mention is this was on a giant vibration table, so all of that vibration with over 250 pounds of wet concrete was very stressful for these 3D prints. But it did eventually work out, and we got it to finalize. This is the final piece. Are there any questions on that before I get into what we're thinking about for scale, as you mentioned before, which I think was a great question?
Yeah, of course, I have another question. So this question has to do with this partner, Concrete Works, and the obvious fact that you're doing both design and construction together. And so is there still a separation of disciplines there? And is that where Concrete Works comes in?
So when I say partner, we partnered with them on this particular project as a collab. They are experts at this field, and while I did a lot of research with my business partner and whoever I could talk to, whoever I can look at, the experience level for something so challenging to work with, we felt a lot more comfortable partnering with them. And at the end of the day, even if I know how to hammer wood into a wall, I'm not going to build a house because I haven't done it for a long time. And I agree that it's starting to become a little bit more blurred lines when you can create objects that are CNC milled directly and used in the field. But at the end of the day, I think the two disciplines are for sure still separated. Though I think that in the future, I hope in the future, it's not going to be as black and white.
Okay.
So speaking of scalability, this is Toyota's Opera House in Korea. And this is one of the precedents we had when we were first studying. This is a model, but this is the overall shape of this building, and it's absolutely impressive. But it did take a ridiculously long time to build, and I think that if there was a new or a different style of which they could have done this, for sure it could have been either smoother or at least a lot cheaper and less time consuming. So this is all the rebar that they had to figure out how to do, all done in metal and mostly by hand. And then obviously the final looks incredible, but this amount of structure I think can be alleviated both in weight, speed, and optimization. Now, one thing that we were going to do, but we didn't because after speaking with Concrete Works, we realized that there was not need for rebar at this scale, is we started to look at different voxels, like I mentioned before, of which were really good for pouring concrete with either diagonal valleys and tunnels or direct filtering valleys like this octagon here. And we started experimenting with imagining this was like a column instead of an actual table. And this was filled in the entire structure of whatever it is that you were making. Imagine if this is instead of a table, it's like a pavilion with a roof. So that's what we want to experiment with next, with creating either concrete lattices, even though these are metal. Imagine this could be made in concrete, or it doesn't have to be a solid form like it is, or having molds like this. This is a Joris Larman project that are removable molds that are 3D printed versus these are injection molded. So while these molds are incredible, each piece costs a lot of time to make, and the material is really expensive. So I think if we have the right material that could be 3D printed, we could create wild looking lattice structure like this out of concrete, or it could just be the internal section of what it has. The company we've been talking to a while ago is Branch Technology, and they basically create a carbon fiber infused filament that comes out of their proprietary KUKA robot that they paint green, and they can create three-dimensional lattices, kind of like space frames, directly out of the printer. And these, because they're carbon infused, not only are they super light, but they act almost identical to rebar. So we imagine that we could work potentially with a company like this to create an internal lattice system that acts as rebar, not just regular lattice system, but topology optimized lattice system, to have the least amount that you need or the most amount to create the structure or the concrete in the least weight possible, and have a good flowability that you could basically create a rebar and removable molds to make larger projects. This is a design project we did for the competition that they held. We unfortunately got second place, and the first place house is getting built right now. But had we been able to win, something like this could be realistically molded and recreated as a custom house, or something that is not a one-off or a throwaway, but basically something that would be nearly impossible to make otherwise. But we think we can kind of do it with the strategy we're doing, with obvious constraints that need to be
Okay. Well, Diego, now that you've taken the small object to the scale of a big structure, which is awesome, I see that our co-presenter, Jeffrey, is able to join us. So it's
great. I'm finished. So that's
good.
great.
Yeah, that's perfect. Okay.
Perfect.
Okay. So I'd like to introduce Jeffrey. Jeffrey is the CFO of ModelNo, and he has been working for 20 years in solving these type of fabrication challenges, the digital fabrication challenges. And we were just talking about designing and building. So part of Jeffrey's focus is integrating those two. He's integrated them into another company called Because We Can. Such a cool name. So I'd like to welcome Jeffrey to share a little bit about his work with ModelNo. Thank you, Jeffrey.
Yeah, I'm actually the CTO,
Oh, I see.
CFO, but that's okay.
Sorry, your bio said CFO.
Really? No,
It's the fault of your bio, man.
okay. Sorry to be late to this. I got the link 10 minutes before it started, so I wasn't sure if it was even happening, so I do apologize for coming in late. Let me share my screen, and I can talk about a couple different things. But yeah, like you said here, hold on, let me just get my screen sharing 1 second, sorry. There we go. And share this. So, and let me know when you can see my screen.
Now.
Okay. So my background is I'm a licensed architect who, yeah, a long time ago bought a CNC machine and started making stuff, and then just started my own design build architecture firm that's been going for quite a while now, doing all kinds of creative projects around the Bay Area. We did everything that a normal boutique-y small architecture firm would do, but we had an in-house shop with a lot of digital fabrication equipment where we just directly fabricate stuff for our own projects. So one local project here in San Francisco that we did that got a lot of press and that possibly you've seen is this Interval for the Long Now, which was like a salon event space that was like that's out in Fort Mason. So, you know, we did everything a normal architecture firm would do here in terms of like, you know, the design, working with the permitting. This is on federal land because it's Park Service, so working with the Park Service and their approval process, which is very different than a normal, you know, building approval process and at times, and health code, like everything that you would normally do for a space like this. But then we also physically fabricated a bunch of stuff in this project, all off of just a central Revit model, taking models directly out of Revit and straight into fabrication. So we had one truly coordinated model that was for design, analysis, communicating with the client, directly fabricating things for the project. So certain things like, you know, some of these elements like this, there's this bookcase under the stairs, you know, we just laser scanned that staircase to get a point cloud of it and then modeled a bookcase that would fit under because that was an existing staircase that we had to work around. You know, fabricated a unit and it just showed up and fit right in place. So there's like really no shop drawings made of that entire cabinet, because being design build, we don't have to go through that traditional like approval process with the shop drawing. So we were able to eliminate like good 20–30% of the labor involved in producing custom elements like this. So we did a bunch of all kinds of little custom details all throughout and stuff. And I mean, there's a number of firms doing this sort of thing. So this isn't super original, but the only really unique thing is how we were kind of living in the future to some extent, where people talk about how using BIM or using digital models for design, how you could then eventually use those models directly for fabrication, much like Diego was just showing. That's happening, right? Like, and it's been happening for a while in some more prosaic areas of the world. Like HVAC and structural steel has actually been doing this for quite a while now, and now it's starting to get into more kind of creative areas. So did a whole lot of projects and can talk about digital fabrication in this regard. And we started a company where this was like our small design build architecture firm. And then we started a new company that's a product company. And this is more of a, kind of traditional startup kind of thing, where we have like investors and raised money, and we're trying to become basically the next Herman Miller is what we're aiming for, which I know is incredibly pretentious to say, but if you're gonna try to start a product company, you should try to start a product company, right? So instead of being like a little boutique, the reason I say that is we're not trying to be like another boutique, expensive designer label that's making like $10,000 chase lounges or something like that. We're trying to do really like be one of the most sustainable furniture companies around. And part of that is the same thing. Like Herman Miller was actually a pretty traditional furniture company back in like the 30s and 40s. And it was after the war and them adopting, kind of new aesthetics with modern design, but also new materials like bent plywood and fiberglass and new ways of making things, and finding new product niches and such that let them kind of grow into, what they are today. So we're kind of taking a similar tack in some regards. So the three key parts of model number is, one of them is on-demand digital fabrication. So we have a prototype set up now of this like micro factory concept, where for a small footprint and a small team of people can produce a really wide range of products from a handful of very automated digital fabrication tools. So a combination of CNC and additive 3D printing, we're able to produce like, whole product lines out of very small footprint with no held inventory and very little product risk. So traditionally, furniture is pretty horrific when you really get into, like 3/4 of it is internationally shipped. It's the second bulkiest thing behind bananas for international shipping. Like the carbon footprint for shipping couches around the world is massive and terrible and pretty terrifying. So so this on-demand production that we're doing really impacts that a lot, and is able to make us able to deliver something significantly more sustainable. The other thing too is that because of the digital fabrication that we have going, all of this stuff is customizable. So we have a little design studio thing here where you can go in and you can, edit different aspects of the table, change the corners and stuff. It's being funky, of course, because whenever you present on Zoom, that's when things break.
Yeah.
So give me a second. But there it goes. So, I can change corners, I can change materials. I can then change dimensions as well. So I can, customize to the inch widths and heights and depths. But because it's all being digitally fabricated on demand with a kind of automated system that we have on the back end to manage all the data and the ordering, you can get this table in like 2 or 3 weeks from order, even though it's totally custom. And so we have a bunch of products that kind of fill that same idea of, where it's like highly customizable, highly sustainable, modern design. The price points, we're aiming for, again, like I said, Herman Miller. So it's not like IKEA price points, but the price points are like reasonable for what some of the things are. And just working like crazy and coming out with new product like about every 2 or 3 weeks. Because we have no held inventory, traditional furniture company has to, guess what people are going to buy, guess how much they're going to buy, go make a whole lot of it, and then hope that they actually sell it and hold it in warehouses. We don't have any of those issues. We're able to just, test market stuff like crazy, try different things like crazy. So right now we actually have a whole bunch of outdoor stuff coming out with, this is some of the first outdoor stuff that we've had coming with this outdoor line, outdoor dining table and chairs, tables and other things. And we have a bunch of more outdoor stuff that's just about to come out. So some of these things, like this chair, for example, it's a wooden base with a 3D printed seat. And right now we're having this be pretty basic because we don't want to confuse consumers too much, and we're still figuring out the best way to offer this as an option. But behind the scenes, like with our CAD model and everything, we can make that seat ergonomically fit you perfectly if you just tell us 1 or 2 things about your body, right? Because the seat pan part is getting 3D printed, it's getting made on demand. It can be customized just as much as anything else. And when we first started out, we were actually offering things with like a lot of custom options, and it was really overwhelming for most consumers. So we actually pulled back how much flexibility we're offering. And so there's a lot of space here that we're exploring in terms of, what kind of conversation do we have with the customers and such. To start with, we've been doing a lot of direct to consumer stuff like this, but we are also working on a line of sustainable retail store fixturing, because retail store fixturing is again, like just a total disaster. It's all, melamine, and it all winds up in a dumpster whenever they clear the store out. And so we're working on a system of where it's possible to maybe, ideally you could just compost everything when the store changes over, right? Like all that display stuff can just go right into the compost directly. And we're also starting to look into a lot more like hospitality stuff as well. Like we have some stuff that people have already been using in that regard. Like there's this chase lounge that we have, big fancy chase lounge that we have that has already been bought to be used in like some hotel lobbies and stuff like that. And these are again available in like custom sizes and different materials and things like that. So we're looking at taking this and making it into more of a sectional, and for hospitality use. We're adhering to all like BIFMA standards and stuff for a lot of our stuff, so it can be used in a commercial environment. It's not like just residential grade. A lot of the stuff is commercial grade. And working like crazy. We had to build our own. I was going to show you a cool video if I can find it. Here we go. Of we built our own 3D printers to be able to do some of the stuff that we're doing. This is a smaller print that's running here, but we have larger prints. Every print that we do winds up getting a little video of it made for troubleshooting, so we can watch and make sure everything's going on right. And so we're building our own 3D printers to be able to do this. We're working with Oak Ridge National Labs on some of the material science and some of the printing technology. They're the people that did the 3D printed boat and the 3D printed car. There's a large additive manufacturing lab that's part of the Department of Energy out of Oak Ridge that has a bunch of different things that they're doing in that. And that we've been working directly with them on the materials and trying to do just more and better stuff. So we just moved. We're going to be having an open house probably next month. We just moved to a bigger, better production facility where we're kind of building out the first like real microfactory sort of setup. And the hope is as things scale and we have more sales, that we'll be opening up microfactories like just outside of some other major urban areas like LA and New York and Chicago. We've been surprisingly getting a lot of orders from Chicago, which is great. So, and again, that helps us get that, this core idea that we want to be down to this like 2-3 week lead time on everything, even if it's custom, is part of that. So that's kind of it in a bag. There's 2 other big things that Model Number is using. Obviously we're doing a lot of digital fabrication. Another big thing that we're doing is it's all, computational parametric design, obviously, because we're doing these like, wildly customizable, flexible thing. I can talk more about that technology or the digital fabrication technology. And then the third thing is the more prosaic, just like we have a really tightly integrated marketing, design, and production team, which a lot of furniture companies don't. A lot of furniture companies like Restoration Hardware is just like 90% marketing with a little design office and all the production is elsewhere. We're not. We're trying to be this like really integrated and think of it more as a product fashion company, where we're like test marketing stuff and driving stuff. There's some great examples of some not so sustainable, but kind of fast fashion apparel companies out of China that have really similar models to kind of what we're doing on that end of things, where it's like really tightly integrated little groups They're just constantly coming out with new product all the time, really rapidly, to figure out what's going to sell, what works well in what markets and things like that. So that's kind of
Wow.
that's kind of the whole picture of what we're up to. Sorry for it to be so compressed. I was,
No,
you know.
we're the ones who should apologize because you didn't have that much time to present, and you're incredibly articulate. And it's so interesting what you did. And kind of, I'm thinking about it in conjunction with what Diego presented. And so, of course, the context here is architecture. Basically, the profession is focused on doing a lot of custom products. Each project is a custom product.
Mhm.
And we're looking at a future where, although things about them can be customized, like the ergonomics of the chair to the individual customer, that the logic of it is the logic of it is integrated with technology in such a way that it can be more or less mass produced.
Yeah, it's interesting because, like, yeah, it used to be that, you know, that like, yeah, it's really intriguing because, you know, the manufacturing and construction were wildly different and are starting to kind of blend more, so to speak, right? And there's still some things that are really different about the two worlds. So like, one of the shocking things with the furniture startup is when we started out, you know, I'm coming from an architecture background, coming from design build background, coming like more like what Diego was showing, right? Where it's like, okay, we're making one of these and it's really special. It's really awesome.
Right.
And, you know, the first successful chair, the first successful table that we 3D printed when we built our first giant 3D printer, you know, we printed it out, and one of our lead designers, who comes from an industrial design furniture background, is like, yeah, this is awesome. Look, we're all oohing and awing over it. And he picks it up. He's like, hey, this is great. And then he takes it and he throws it on the ground as hard as he can, like on the concrete slab in front of us all. Because he's like, yeah, it has to work. It can't break if you drop it. And it's one of thousands. Like, it's not special. You know?
Yeah.
And it's like a very different attitude, you know, out of the gate, where it's like, oh, okay, yeah, this is a really different problem that we're solving, a really different outlook on this, right? Like, you know, even though it's, you know, so there's a lot of differences that happen too still between the two worlds, you know.
So Diego walked us through like the logic behind the voxels that, you know, we're using a very small scale in the shoe, but I mean, of course, could be at different scales.
Yeah.
And so I see the logic, the science, if you will, there, and the fact that you guys are both architects. So it's not just a coincidence that you guys are developing things like this, because the architecture profession is based upon solving problems in a rational way. So these are very rational solutions. And it's striking how beautiful they are at the same time, that they're incredibly aesthetic. And I think, and also with the voxels, I was thinking that there's something kind of organic about the way that the design emerges from the process of using all this logic, like the beautiful curves and the angles of the table, which are really just based upon doing it in the most efficient way possible. But that's the way nature does things, in the most efficient way possible, and we perceive them as being beautiful.
A key thing that digital fabrication really opens up that's interesting is that you know, so you probably already know, this is probably already obvious, but I'm sorry, this is something I usually talk about when I go through this. Is it used to be a long time ago that materials were really expensive, but labor was really, really cheap. And when that was the case, you had things like Art Nouveau and Art Deco happening, you know, where it's like, okay, all this stuff is amazing and decorative and crazy, but it's all made of plaster, right? It's all like, you know, because we're really cheap materials, but we have tons of labor that we can throw at it. And then after World War II, the construction industry shifted the other way, where labor became expensive, but materials became really cheap, right? So now, you know, you've got everything hyper optimized for the least amount of labor possible to put up a house or to put up a building or facade or what have you. With the digital fabrication, that's starting to tip back again, because you can have the labor be, you know, you can have, like in this case, you know, we're making furniture and each one can be unique and it doesn't cost extra because of how we're setting it up to be made, you know, off the CNC machines and off of the 3D printers. that it really starts to open up the ability to make things that might be more suitable for like, you know, the strength and dynamics of it, right? You know, because before, sure, you could make something like a super organic frame that would be perfectly optimal out of steel. It's just the labor to do that would be so expensive, and the calculations to run it would be so expensive that nobody would really do that except for like on a Zaha Hadid, you know, crazy high-end project. So, you know, it just never happened. And instead your engineer just gives you another moment frame, and you have another moment frame, and it's like all the other moment frames because that's what's affordable to do. And now everything's a box, you know? And so what's interesting is some of this technology is opening up a lot of opportunities to introduce much more interesting forms and shapes into things again, and have it not cost an arm and a leg, you know?
That's
which is
awesome
really
for the
exciting.
profession of architecture. Yeah,
Yeah.
absolutely.
I completely agree with that. That's something that was really challenging as a fresh student out of school. When I first came out, I was, you know, obviously trying to make a lot more interesting stuff that you normally don't see. And, you know, it always just gets beat up. People are like, why would you do that? It's a lot more expensive. And it's like, well, it's more interesting. Well, it's expensive. And now, like he said, it doesn't really matter when you use additive manufacturing, because I mean, the only expensive part is like putting in those factors into the parametric design. But once you've already done that, it's all set up.
Yeah, well, it's interesting you talk about it. Well, it's more interesting because it's like, if it's not based upon some rationality, like what does the structure need to be and how can we do this with the least amount of material, then you're making it more complicated just for the sake of complication. But so the interest is like something that's being added on unnecessarily, as opposed to something that is evolving from making it practical, actually. And that makes it more interesting. I think in the end, just looking at the potential of this technology, I think that it begs the architecture profession to rethink the idea of each building being a custom product in the same way that they are now, where each one is individually designed. And the marketplace, I think outside of architecture, is going already in that direction with more and more modularity. But the modularity, unfortunately, is mimicking the boxiness, which Jeffrey was just talking about. And it doesn't need to. And you guys are the inventors. And I think that that's an opportunity that all architects have with the training that we have, is to invent ways to do what you guys are doing. And even if we don't do it ourselves, to integrate your technology and your thought process into the work that we do.
I gotta run here in a moment. Totally open for more questions. Sorry that I gotta cut it short.
Yeah.
I wish I had more time to hang out, but I gotta go in just a
Okay.
couple minutes. So
Yeah, perfect. Thank you. So
no. I'm not. I can take more questions. I can hang out for a little bit longer, but I gotta say I gotta wrap it up, and I'm really sorry. I wish I had more time.
no, perfect. So I'm inviting everybody to ask questions.
So David said a really quick question. This is for both Diego and Jeffrey. Jeffrey, you talked a little bit about your limitations as far as like the industry and a lot of moving product from overseas and things like that. And I'm sure that can be cost prohibitive, you know, in certain situations. But I was thinking more of on the technology wise, and I wish we had more time to get into more of like Grasshopper, you know, whatever you're using as far as comp and gen design or like plugins.
It's pretty much like 90% Grasshopper. Like
gotcha, yeah.
Right, like it's like you know, you pull back the curtain and it's always Grasshopper. Like at least that's the level behind everything.
It's just a sea of spaghetti. Yeah, I get. Do you see any limitations as far as like whether it's Grasshopper or anything else, that ideas that you may have in your mind, but the technology right now, it just is not able to get there.
Totally.
You know,
yeah. So we're using a number of different things. So like the stuff that you saw, like the interactive thing on the website that lets you customize it. That's Grasshopper running through something called Shape Diver that lets you take your Grasshopper and push it all the way to the web so somebody can interact with it. It's okay. It's not great. it's because it's server side, it's always slow no matter what you do. It'd be much better if it was client side, but in order for it to be client side, you have to essentially write your own little 3D apps that would run in the browser. Theoretically, somebody could make a CAD program that does that sort of thing, right? But there isn't. There's not a good platform, unfortunately, for a lot of this stuff. You get into the voxel-based stuff, like sure, you can do it in Grasshopper, you can do voxel-based things, but like there was Monolith, there's a couple programs that people have tried to do around voxel-based design stuff, but voxel's really new. And again, there isn't like a good CAD platform for doing crazy voxel-based stuff right now. So like one example is like there's 3D printers that can do things where the materials would vary within the print itself. So like some parts hard, some parts squishy, different durometers in the object in different ways. The shoe companies are doing this for like making custom soles and stuff like that, right? So the CAD of modeling something where like its internal properties are changing at different parts of the inside of the object is a total nightmare right now. Like there's nothing, like all the CAD packages are assuming that your thing is a solid shape with, and the inside's like monolithic and uniform, right? When it might not be, right? Like you might have different material properties in parts of the object. Some of the stuff that we've been playing around with, we don't have the printing technology in-house to be able to do it yet, because the printers to be able to print these kinds of objects cost like $500,000. And if you're making furniture, that doesn't work out unless you're selling a lot of furniture to where you can then go convince the investors to give you $500,000 to go buy that like giant printer that can do the crazy materials like I'm talking about, where it can do like dual materials in one object and stuff. But there's actually some software that we've been playing around with and using for some product design called Houdini, which is made for the movie industry. It's more parametric than Grasshopper. It's awesome. It's completely great. It's phenomenal, but it's also a nightmare learning curve to learn, and was never intended for actually making physical things. It's made for making special effects for movies. So, you know, you were talking about the sea of spaghetti. Like in Houdini, I have a routine that makes like really awesome, like, let's see if I have one around. It makes really crazy dual mesh objects that are like interwoven meshes, and you can control like how the meshes interweave and how many legs they have and like all this other crazy stuff. The script, if you will, like the Grasshopper routine, the first third of it does the modeling, and the other 2/3 of it makes that model into something that you could actually 3D print, because the meshes that Houdini produces are so incredibly messy, because it was never intended to be something that would be manufacturable, because it's something that's just rendering. It's just to look cool on a screen. Like, doesn't matter if it's messy, right? So like we're Frankensteining together our own stuff, you know, based off of these different parts and pieces. It just like to your comment, Dave, on the modularity problem, you know, like prefabrication and architecture in general really struggles from the fact that there's no good platform for prefabrication in architecture. Like Revit is terrible at it, but everything else is worse. So what do you do, right? You either have people that are really clever at Revit that can do the modeling that's necessary to support fabrication, or you desperately try to use SolidWorks and fail, which I've seen happen numerous times, right? You know, here we are making furniture, we're using Grasshopper, Fusion, Houdini, and a little bit of Blender even, and sometimes, you know, and again, there is no good. I wish there was a really awesome platform for us, you know, like something like have you seen Onshape? It's some of the original SolidWorks founders got together and are making like the next generation mechanical CAD tool called Onshape, and it runs entirely in a browser, you know, and is really impressive what they're pulling off entirely within a browser. And they're trying to make like a universal browser-based platform for mechanical design, right? Like, okay, that would be amazing if something like that existed for these more complex construction projects or more complex organic kinds of forms, but it just doesn't, you know? So we beat up against that a lot. To answer the question, yeah.
Yes, I want to give Diego a chance to talk for a second.
Yes. Yeah, I mean, I agree with literally all that. I think Houdini is pretty cool. We can start messing around with that in Blender a lot. I think something like Shape Diver, which is, like you said, is like a server base. It's really awesome. It's one of the first ones, but it's not. I mean, I don't know what the speed is like in comparison to what I've been using it on the user end, but it sounds like it's not quite there yet. I think the fact that we have to make our own tools is one big problem, because all the tools are out there are generally for some other industry that is more expensive, and for that reason, that tool exists. Until that industry is the industry that we're in, we're going to have to piggyback on the animation and all the other you know, industries that start to create these awesome things. Another thing is that you know, while you can make Grasshopper amazing, what everyone doesn't understand for the most part is not everything is 3D printable or CNCable. Like it's just inherent limitations to material or even the tools to get in there. All that kind of stuff, you can make something that looks amazing and watertight, etc. But at the end of the day, like Jeffrey probably knows the most, it's like if he's filming every print because of one little thing that can go wrong, imagine there's 1,000 little things that are going to go wrong, and it could change because of the humidity in the air in the factory that day, like stuff like that. I mean, that's the limitations that people don't understand at first. But I think it is starting to become a lot easier to speak between all the languages. And one thing that I've recently been playing around with, which is Entopology. It's completely different, but it's its own version, and it is very powerful because it can take on an extreme amount of triangulated surfaces and meshes, and just completely add what we're referring to as Grasshopper type indentations within seconds, and it doesn't even slow down whatsoever. It's relatively new software, but it's a little bit more for product design. I think it would be really cool if it was made for larger furniture scale.
Yeah, I agree. Entopology is really cool. It's really neat stuff. Yeah.
But there are companies making stuff like that like every year now, so it's kind of cool.
Sorry, I didn't mean to interrupt you. I just want to give Mark an opportunity to ask a question that he posed in the chat.
Oh, sorry.
Hi, Jeffrey, are you when we custom like something from your product, it's like one piece of art basically?
Yeah.
When I purchase something, it's like a blockchain, right?
No, it's kind of every product. We have this thing that we call a genome, where there's a code of numbers that gets actually engraved on every product. That code of numbers represents that product. So that if you want to make another one of those, if you give us that code, we can make another one of those, no matter what custom options you picked. So every product gets a long string of numbers. Let me, I might be able to find one. Hold on, I'll be right back. Let's see, I think we have one sitting around.
Yeah, that's what's also pretty impressive is that, you know, if you have an old piece of furniture that breaks, you can't necessarily like print it again, or you can't make it again. But if you have something that you printed, you can take it off like a digital shelf versus like, I mean, in all industries, cars specifically, like old cars, they have one piece that breaks. And unless that file is digitally archived, they probably haven't even made that tooling to pour it again.
Like this is like a bin, trash bin like thing, but see there's a number on the bottom there.
Yeah, I see that.
And so that number is this object essentially. So if you take this number and you feed it to our production system that we're building, that's like it's a fabrication server using Rhino compute essentially. If you feed it this number, it will feed you this object ready to make another one. So
literally the model number.
What's that?
Literally the model number.
Literally the model number. Yeah. Yep. That's the shtick. You got it. So yeah. So not exactly like blockchain, because it's not that number is not like some kind of unique traceable hash to that one single object, right? So like, you know, if you had 50 of these, they'd all have the same model number on it, except for the last digit. That's like the order that of which number of it is. But that long code of numbers is just the capturing of what that object is. So like you said, though, to point, in the future, if something breaks, if you can give us the number, we can give you a replacement part and know that it's going to fit perfectly, even though the thing was custom.
Interesting. Thank you.
Right.
Yeah, no problem.
It's all computerized.
Yeah, and then with the manufacturing lab, Cooper had a question on manufacturing lab.
Oak Ridge National.
Oh yeah, the Oak Ridge National Labs. Yeah. So Department of Energy has a large additive manufacturing research group that is in Oak Ridge, and they're doing a lot of different crazy things. So if you saw recently, they 3D printed they worked with a university to 3D print like an entire boat. They 3D printed an entire car body. They've done a number of other like really large things. They have a couple of really large printers. They're working on a like concrete printing system that they're trying to leverage into like making building structures and stuff. They're trying to do like 3D printed nuclear reactors for the Navy and like other crazy things like that. So so that's the manufacturing lab that we're working. We're specifically working with them on some 3D printing technology and on materials and on the recyclability because we're able to take a lot of our stuff and grind it up and reuse the resin to print new stuff. So we can do a closed loop on the recycle for the product. And so we're working with them on that and on some carbon footprint stuff. So
Yeah, and I really applaud you for the thinking, the rationality that you have with the sustainability, the problem that you've identified in terms of the unsustainable aspects of the way that our products are manufactured and delivered now. And it creates more of an imperative to make a change. On the one hand, there's the opportunity to make the change because of the technology, but in fact, there's really a need to make the change. The status quo is unsustainable.
So,
Yeah.
sorry, Dave, that actually sparked another question in my mind for both you guys, for Jeffrey and Diego.
okay, last question for you, though. I really got to run. I'm sorry.
Yeah, sorry.
It's okay.
Yeah, you guys have been great. Thank you.
Yeah, so we all know what's been going on with the industry as far as like lumber prices over the last year and change. How does that translate to the materials that you guys are using? Has there been a huge spike in resin, other things like that? Or?
Not for us yet, thankfully, no. Because the resin for us is our resins. We're using special formulations of PLA that were getting made for us by Tech Mirror and NatureWorks, and they're by working directly with them, it's all agricultural, second use agricultural waste. So it's all stuff left over from making sugar from sugarcane and corn. So for us, there's been no disruption on the resin side. And on the woods, the fancy hardwoods that we're using are all domestically sourced, sustainably domestically sourced, beech, walnut, oak. Thankfully, so far, those haven't really been affected too much by prices. Part of that is because the lumber prices for construction lumber were impacted for a lot of different reasons that didn't actually impact furniture grade hardwood. So thankfully, so we were lucky so far.
Yeah, we're not making enough volume for it to really affect us either.
Okay, are we ready to wrap up now?
I got to run.
Okay.
Thank you so much.
Thank you. I really, really want to thank you guys. What you're doing is brilliant. And I want to see it having more effect in the architecture profession.
Thanks for having us.
Okay.
Yeah, thanks for having us.
Thanks for everyone for participating and joining in. Okay.
Yeah.
Thank you.
Thanks for presenting, guys. Appreciate it.
Thank
All right. Take care. Bye.
Thank you. Okay. Bye-bye.